We present Joker, a new method for conditional 3D head synthesis with extreme expressions. Given a single reference image, we create a 3D reconstruction with a reference identity and a new expression. The target expression is controlled with parameters of a 3D morphable model, 3DMM for short, and text prompts. This multimodal control is essential because 3DMMs alone fail to define subtle emotional changes and tongue articulations. We found that text prompts are a user-friendly control signal to solve these ambiguities. While fixing the general pose through the 3DMM, text control can be used to specify emotion-related expression subtleties and tongue articulation. Our method can synthesize a wide range of extreme expressions and generalizes well to out-of-distribution samples, like sculptures, heavy makeup, and paintings. We found that existing single-shot 3D head avatar methods fail to synthesize extreme expressions. The reconstructions show clear artifacts, do not follow the target expression, and have a high identity gap. In contrast, our reconstructions excel in terms of expression fidelity and identity alignment. Our model can also be driven by expressions extracted from other subjects in a cross-reenactment scenario. To the best of our knowledge, we are the first to achieve view-consistent tongue articulation. Even for highly challenging reference images with strong side views, our model produces plausible results. Our method consists of two components: a 2D diffusion prior that predicts images of the reference identity with novel poses and expressions, and a distillation procedure to lift the prior predictions into 3D. Our diffusion-based prior has three parts: a denoising network, a reference network, and a driving network, all of which are initialized from pre-trained Stable Diffusion weights. The denoising network receives noise and text prompts as input and predicts the denoised output images. The reference network takes the reference image and text prompts as input and infuses key and value features from its self-attention layers into the denoising network to ensure identity alignment. The driving network is constructed as a control net, which takes normal map renderings of the 3DMM and text prompts as input and drives the denoising network through residual connections. Our 2D prior differs from previous work as follows. First, we used normal map renderings of a 3DMM to drive our model, which provides dense control over pose and expression. Second, we fine-tuned the upsampling layers of the denoising network while previous works kept it fixed. We found that this improves image quality and identity alignment significantly. Third, while previous methods discard text control, we actively use it to fix ambiguities in the 3DMM control. This greatly improves the synthesis of emotion-related appearance changes and enables tongue articulation, since tongues are not represented with the 3DMM. We compare our 2D prior against current baselines and find that we consistently outperform them. Existing methods show artifacts for extreme expressions in reference and driving images. Instead, our method is robust to these challenging cases, produces more plausible results, and follows the target pose more accurately. Please refer to the paper for more results. To lift the predictions of our prior into 3D, we develop a new distillation procedure. We use a neural radiance field, NeRF for short, to present the head in 3 dimensions. Our distillation procedure consists of two stages. In stage 1, we optimize the NeRF against target images generated with our 2D prior. The target images are frequently updated based on the NeRF renderings to improve view consistency. In stage 2, we generate the target images only once in a multi-step denoising process and optimize the NeRF until convergence. In detail, for stage 1, we sample 100 discrete noise levels from the noise schedule of the diffusion prior. We initialize the NeRF and render it onto multiple target views. We add noise to the renders according to our discrete schedule and use our 2D prior to denoise them in a single inference step. The resulting images serve as targets to optimize the NeRF for several iterations. This procedure is repeated to distill a consistent 3D representation. In contrast to previous work, we follow a discrete noise schedule with progressively decreasing noise levels instead of randomly sampling them. Also, we optimize against the target images for several iterations before updating them, while most existing methods generate new target images for each NeRF update. We found that if we follow stage 1 distillation for all noise levels, it converges to consistent yet blurry results. This is because the NeRF optimization against the target images introduces a low frequency bias into the distillation procedure. Please refer to the main paper for more details. To avoid this effect, we interrupt stage 1 at an intermediate noise level and introduce stage 2. In stage 2, we generate the target images only once and optimize the NeRF against these fixed targets. We render the NeRF under the target views, noise them, and predict the target images with our 2D prior, this time in a multi-step DDIM denoising process over the remaining noise levels. We then optimize the NeRF against these fixed targets until convergence. Compared to only applying stage 1, this two-stage procedure improves the reconstruction quality greatly. We compare our distillation procedure against the two state-of-the-art baselines Prolific Dreamer and Image Dream. Further, we evaluate using stage 1 and 2 only, respectively. For both baselines, we replace their 2D diffusion prior with our own model for a fair comparison. Prolific Dreamer introduced variational score distillation and fine-tunes a diffusion model to approximate the NeRF renderings during distillation. However, we found that it does not converge stably for 3D novel expression synthesis because the fine-tuned diffusion model fails to estimate the NeRF renderings accurately enough. Image Dream uses a diffusion prior that predicts multi-view consistent images to perform multi-view score distillation sampling. While it converges more stably than Prolific Dreamer, compared to our method, the noise levels are sampled randomly during distillation, which yields artifacts. Performing stage 1 of our approach only resolves the artifacts due to the discrete noise schedule, yet it produces blurry results. If we only use stage 2 of our approach, we obtain sharp yet inconsistent reconstructions with semi-transparent artifacts. Combining both stages converges to consistent reconstructions with high fidelity. The differences between stage 2 only and our full method are particularly apparent for the tongue and eye region. In summary, we contribute a diffusion-based 2D prior for extreme expression synthesis which generalizes well to out-of-distribution samples, and a new 3D distillation approach that achieves a high degree of realism and view consistency. Thanks for watching.